Hi, I am Corsin.
I'm Stephanie.
And we're going to explain to you in simple terms the main statements of our paper. The main question that we want to answer is, could it be that physics is actually discrete? To explain to you what this means, let's make a simple example, namely the bit. Classically, the bit can have two different values, namely 0 or 1, or yes or no, or however you call it. In the quantum case, however, the so-called quantum bit doesn't just have values 0 and 1, but a whole continuum of values represented by points on the surface of this ball. This is what we call a quantum bit, or it's also known as a qubit. Now one might ask the question, instead of this system being continuous like this ball, could it be that it's actually discrete, but we just don't see it? For example, could it be that the quantum bit is actually replaced by something which looks like this? This has finitely many corners, which then would represent the finitely many states of the system, and this would be what we call a discrete system. Well, maybe it's not that extreme, but we have a quite high measurement precision, but we cannot distinguish between a completely round one or one which is just almost round, like this 100-sided dice. So the question is, instead of the system being round like a ball, could it have this shape, or even one of the more discretized ones like these?
So the result of our article is to show that there is a simple postulate, an information-theoretic reason, so to say if you want, that if we accept this postulate, then in fact any discretized version of quantum mechanics is ruled out. So let me explain what this postulate is, and to understand the postulate, let me explain what is a measurement. So a measurement, you can think is just a device. Maybe it's a scale or something else that you use to perform measurements. And well, you can think that it just takes the thing that we want to measure as an input. So it has some input state. And well, we want to learn something by making the measurement. So the measurement also has some measurement outcomes. Okay, so for example, how heavy the object is. Okay, so there's several possible measurement outcomes. And I'll just label them 1, 2, and 3. Okay, so we could have many more measurement outcomes, but let me just make an example. So in addition to observing a certain measurement outcome, for example, how heavy is this object? Well, the measurement device also has an output state. So this is whatever happens to the object after we make the measurement. So when making a quantum mechanical measurement, it can happen that the output state is not equal to the input state. Okay, because a collapse occurs, and conditioned on which measurement outcome we observe, we get a different kind of output state. Okay, so for example, just for purpose of illustration, the famous Schrödinger cat example, we don't know ahead of time what's in the box. There's some cat is in some superposition of states. We make a measurement and we find the cat either dead or alive. Okay. But after we make the measurement, well, there's a collapse, so the cat is definitely going to be dead or definitely going to be alive. So when making a measurement, we can ask ourselves, can we in principle gain any information by making the measurement? So do we learn anything? Or is it possible that someone already knows the answer and we are just verifying? Okay, so the question is, do we gain information? And the notion of information gain in a measurement means the following. So information gain occurs if I cannot predict the measurement outcome. So this means that multiple measurement outcomes can in principle occur. Okay, so if measurement outcomes have some probability, and let me just make an example. Let's say that I have some input state such that outcome 1 has probability half, outcome 3 has probability half. Then when we make the measurement, we gain some information because we don't know in advance what's going to happen. We could get either 1 or 3. Okay. So in quantum mechanics, if we gain information, so multiple outcomes are possible, maybe the cat could be dead or could also be alive, then in fact a collapse occurs and the output state is not equal to the input state. So this means that information gain causes disturbance. We change the system by making the measurement. Now our postulate says exactly the opposite. So we're going to postulate that no information gain causes no disturbance. And no disturbance means that the output is equal to the input. So in this little example, it means that, well, not 1 and 3 can occur, but we can perfectly predict what is going to happen. So let's say that 3 occurs with probability 1, and the other ones cannot occur. So this means that if we make the measurement, nothing changes. Okay, so if you think back about the example of the cat, if I look inside the box and I find the cat either dead or alive, then if nothing happens to the box in the meantime, well, if I'm going to look inside the box again, I find the cat in exactly the same state as it was before. If it was dead, it's still going to be dead. If it was alive, then it's still going to be alive. So this is our postulate. So maybe if you think about the example of the cat, maybe it's intuitive that you're not going to resurrect the cat while making another measurement. So it should be said that quantum mechanics and also classical theory do of course satisfy this postulate. In fact, they satisfy this postulate in even stronger form than we assume it here. So in quantum mechanics, if I gain little information by making the measurement, meaning that some outcome doesn't occur with probability 1 but with very large probability, close to 1, then also there's little disturbance. Okay, so if we now accept that no information gain causes no disturbance, then in fact we show that any discretized version of quantum mechanics is ruled out. So if we accept this, then it cannot be that deep down we are actually discrete and we just don't see it. But actually we must either be round, like a quantum system, or we are in fact completely classical. We already know from experiments that the nature cannot be purely classical. So you can think that this means that in fact we are not discrete, we really continue.